So, as Sylvain mentioned, I worked at Google for YouTube's video classification team for a few years, and I thought I'd share a little bit of what I learned there today. Specifically on using a mix of knowledge graph and deep learning together to improve search and discovery. It's a complex problem because you have billions of videos on YouTube, hundreds of millions or billions of users, and you want to recommend the best content to everyone. So you all use YouTube, I guess, pretty regularly, and if you don't log in, this is the kind of page you get. Generic recommendations, trending videos. These videos are likely to appeal to a wide audience, but not specifically to you. Okay? So for example, here we have this story about Mamadou Gassama a few days ago who saved this child by climbing a building. It's a very nice story, quite touching, so a lot of people watch this video, so it's recommended 5 times on this homepage. And, well, I guess I watched one. I probably won't watch 30 minutes of that or more. So if I log in, this is the kind of page I get. So in this case, it's like math, genetic algorithms. Whose homepage looks like this? Raise your hand. Right. Oh, I would expect more. OK, so I guess I'm a geek. So YouTube has figured out the kind of topics I like, and we'll see how this is done. So the first big component of recommendations is in all those large systems called collaborative filtering. And you've probably seen this before. I'll go really quickly. YouTube has a huge matrix of users. Every row is a user, and documents or videos in all the columns. And the point is to make a match, figure out or guess who is going to like what. And we already have a few of these cells that are filled in. Okay, so we know that the second user liked the second video and so on. But it's an extremely sparse matrix. I mean, most of the cells are empty because every single user has only watched a tiny portion of YouTube's catalog. So that's the main problem that we have to figure out. And if I look at, for example, the second user, I log on, or that user logs on, and we have to guess what that user wants to watch. Well, we can see he liked the second video, and we can look at who else liked that second video. So user 3 and 5 did. And what else did users 3 and 5 like? Well, they also liked the video number 3. So it's likely that user number 2 is going to like that video as well. So that's what we recommend. That's the core of collaborative filtering. It works incredibly well. I mean, it's used all over the place at Spotify and Facebook and all that. That's one of their core components. And hopefully, the user is happy and gives a little bit more signal that will contribute to train the system. Now, it turns out that YouTube's research team actually published a paper on precisely how they implement this. In September, I think, 2016, pretty recently, they published this paper called Deep Neural Nets for YouTube Recommendations. I recommend you read it. It's actually really interesting. It turns out they just use a neural network. So at the bottom, you feed the neural net the previous videos that the user watched. You also feed, some of the searches that the user did, maybe what country he is in, or the age if we have that, or gender, or even combinations of all of these features. And it's not actually a very deep neural net, as you can see. It's pretty wide at the bottom, and then it gradually goes up to the top, where we predict what the next video that the user is going to watch. We try to predict that. And it's trained on all the user's history, so we know what they watched in the past, and so we can train the neural net based on that. The top part is a little bit complex because mostly for performance. It's explained in the paper. I won't get into the detail here. But it's basically a fairly simple neural net. And it works really well. Now, the famous problem with collaborative filtering is called the cold start problem. It's the fact that if you have a new user or a new video, well, there's not much signal to train the neural net with. So for example, think about that fourth user. She only watched a single video, and it turns out it's a video that nobody else watched. So what do? Well, you can't really recommend anything at that point. And there's the same problem for the video. This is a new video. Only one person watched it, but it's somebody who didn't watch anything else, so no signal. And you get really poor recommendations in this context. Like the video gets sent out to either nobody or people who don't care about the video, and the new user gets really poor recommendations at the beginning. So how can we fix this problem? Well, if I were to tell you the topics of the videos, that would definitely help, right? If I can tell you that video number 1 and 4 are Daft Punk videos, and video 2, 3, and 5 are wingsuit flying videos, okay, now my matrix is much smaller, much denser. So I can actually look at the 4th user here and see, oh, well, that one video she saw is actually a wingsuit flying video, so maybe I can recommend more wingsuit flying videos. And similarly, the new video happens to be a wingsuit flying video, so I can recommend it to all users who are already fan of wingsuit flying. And boom, hopefully, everybody's happy, and this solves the cold start problem. So it's it's a well-known solution to the cold start problem is to actually understand what the content is about. And so the rest of the talk will be about how we do that, how we actually understand what the topic of each video is. But so before I do that, if you know what the topic of the video is, how do you actually feed it to this neural net that we saw earlier? I actually don't know how they do it. I would assume that what they do is, at the bottom, they just add another input, which would be the topics of the last videos, or all the main topics that the user likes. And that's just a new input to the neural net, and hopefully, during training, it will pick up the fact that, well, this user, okay, she didn't watch much videos, but the one she watched was wingsuit flying, so let's recommend this or that. Okay, so now we want to figure out what the topics of the videos are, and there are many signals that you can use to figure that out. And I guess the most obvious one is, since it's a video, well, maybe you look at the images and the sound and try to classify the video. And this actually works pretty well if you train a deep neural network on tens of thousands of videos that were already classified by humans as being basketball videos or wingsuit flying videos and so on. The deep ConvNet will eventually get pretty good performance. And the team in the VCA team in Mountain View actually did this back in 2014 in collaboration with Stanford, I believe. And I thought I'd show you a quick video of what they did back then. So that's 3.5 years old, but it's still impressive, I find. So it was trained on 400 sports, and it shows you the top 3 sports that it believes the video is about, strictly based on the images. In this case, it doesn't take into account the sound. And here it says basketball, and then wheelchair basketball with 88 or something confidence. It's pretty high confidence. So you can see it's getting really good performance. I like this one where they punch each other out. So this is MMA, very, very high confidence. Even when it gets it wrong, creaking and so on, it's actually not that bad, right? It's in the right ballpark at least. So usually the right solution is in the top 3. Here, if you can see, the little ball says model aircraft and then back to golf, because at one point all you see is this little black dot in the sky, and model aircraft is a pretty good guess in that case. And at the end you see a few mistakes. It says softball and so on, so it's not perfect, but it's pretty good. Now, ouch, that must have hurt. Okay, so, and this guy I think punches himself out. Yeah, okay. So the point is that you can actually get pretty good performance, but it's tremendously expensive in all senses. You need to build a big data set. You need to train large models, convolutional models, and deploy this and all that. And all that to get fairly good performance, but not tremendous performance. And when you look at the video, usually most of the information is actually in the title and the description. So let's use VCA when it's useful, but let's also use the text. I mean, consider this video about this guy doing some wingsuit flying over Dubai. You can probably recognize Dubai on the image up there. There's the famous Palm Islands over there. So based on just the image, you probably could have guessed the title. But hey, it's in the title, right? Epic Wingsuit Skydive Dubai. Why try guess when it's actually written? So wingsuit actually appears 3 times. You should be able to guess that. So a big signal is actually just text. And how do you do the mapping from the text to the topics? And before I answer that, what vocabulary are you going to use? When we train the neural nets, we train them on about 400 sports, or you train them on video games, perhaps a few hundred video games, but it's not like millions of topics. And when you look at YouTube videos, you can figure out that there are millions of topics that people enjoy. So you don't want such a small vocabulary. You want a big vocabulary. You want to be able to classify all sorts of topics. And so where do we find this vocabulary? We could just write down a huge list of topics. That'd be a little bit cumbersome. So instead, we're going to use a knowledge graph. And a knowledge graph, to introduce knowledge graph, I'll first talk quickly about the Wikipedia. That's a whole bunch of knowledge for humans, right? It's just text and hyperlinks and pictures and things like that. It's great for humans, but probably not that great for machines to go and parse this, right? The information is really meant for us. But you may never have noticed this. At the very bottom left-hand side, there's a link to Wikidata. And Wikidata is this other project that actually has a lot of structured information as in the form of an open source knowledge graph. Now, of course, Google uses its own internal knowledge graph now. But yeah, if you want to try this at home, you can try and use Wikidata. It's pretty good. So if you click on this, you reach Michael Jackson's topic page. So he has his ID, he's Q2831, and you have all sorts of information about this person, and it's structured information, very easy to go and fetch through REST requests. And if you look specifically, for example, it says that he was an instance of human, which I guess, yeah. And the genre is pop music and soul music and dance music and so on. So it's structured in the form of statements, like a long list of statements. And more specifically, the way they are organized is in so-called triples. There's the entity, that's another name for topic, such as Michael Jackson. There's a property, for example, instance of, or a music genre. And then there's a value for that particular property for this entity. So yeah, Michael Jackson's instance of Q5, which is human. And you can organize a huge graph using these triples. And for example, you have Michael Jackson, whose place of birth is the city Gary, and you also have the GPS location of that city, and so on. It's amazing, actually, what you can query on this website, on query.wikidata.org. If you go there, and I really encourage you to do so after this talk, you can actually write SparkQL queries. This is a special language that kind of resembles SQL, but to query graphs. And in this particular case, for example, I'm saying, I want all the triples that have the following template, where we have the entity Q2831, that's Michael Jackson, the property P19, this is place of birth, and, well, I'm not telling what the value is, I'm putting this in a variable, place. Okay, so now this place variable will have the reference to the city of birth of Michael Jackson. And then the second line here inside the select gives me more information about that place. I want to query what is the GPS coordinate of this thing. So eventually I'll get the coordinates, and that's what I select. So this query, it's pretty simple, gives me the GPS location of Michael Jackson's place of birth. The little hashtag at the top, default view map, tells Wikidata to actually display this in a nice map, and this is what you get. You can write a little 6-line code of Python using import requests on the server, and you get the location. There's no more code than just this, so it's pretty simple to use. Anyway, so that's the motivating factor. You can actually use knowledge graphs yourself. It's easier than you think, so I recommend you check this out. And at Google, it's used all over the place. Well, not Wikidata, but their internal knowledge graph. For example, when you search for, say, Paris on Google search, you often get these little knowledge panels on the side, and there's structured information there. This is extracted from the knowledge graph, like the area, the name, the weather, and so on. Inside YouTube, it's actually the same team that was doing the classification that took care of these things at the right-hand side, which are called watch cards. And you can put all sorts of structured information in there. It's not like organic results from search, right? It's actually structured. We recognize that you search for Daft Punk, and we give you the actual list of albums, the list of tracks in there, and so on. So you can get, in terms of discovery, a good mix of organic search and recommendations and structured browsing. Okay, so that's another benefit. It's actually entities you can show to users. Then you can build automatic channels like this one, which has at the bottom things like Daft Punk covers, you see, which we can extract if we've annotated every Daft Punk cover with the entity Daft Punk, that we could put this automatically on this page. and you get some pretty amazing content in there. All right, so back to the problem of mapping text to knowledge graph entities. Well, we know that wingsuit maps to the topic wingsuit flying, although it's not exactly the same name. So one way to do this, simple way to do this, is to look at all the hyperlinks inside Wikipedia. And there are each hyperlink has a name, and sometimes people link to the United States of America with just US, or sometimes USA, and so on. So this gives you a nice list of aliases for each of these topics, some of which you can find on Wikidata itself. So you can do simple text matching. It actually works pretty well. The problem is you can also match Dubai and a whole lot of other things. And the next question is, okay, well, there's a lot of topics, but which topic is this video actually about? What's the central topic? Because if you look a little bit more closely, there's also base jumping, extreme sports, skydiving. So which one is it? Well, you can look at the co-occurrence of topics on the Wikipedia and find out that, oh, look, base jumping frequently co-occurs with wingsuit flying. It doesn't really frequently co-occur with Dubai. So this topic can actually, or topics can vote for each other. And for wingsuit flying, in this case, we'll get a lot of votes. And this way, we can tell that wingsuit flying is probably a central topic in this case. And Dubai is not that central, but it's still in the title, so we won't push it down too much. And then you got things like Richard Schneider, and there is actually a lot of them. None of them actually do any wingsuit flying, so they're fairly easy to rule out. They never co-occur with wingsuit flying. And then you've got some noise like website, Twitter, Facebook. Those all are topics, but they're clearly not the topic of the video. You can rule them out with things like TF-IDF or just frequency, inverse document frequency. And that's it. So first you identify mentions of a topic, then you disambiguate, and then you prune all the noise, and you end up with a pretty good classification. Now, there's more modern approaches now, which are linked to deep learning. And for example, this is an example of entity recognition. It's not actually linking to Wikidata, but just saying, whoa, this is probably a location. And this helps a lot because, for example, if I see Washington, and I know it's a city, like if entity recognition tells me, well, this is a location here, then I can filter in my query and say, I don't want George Washington, or I want a city. And there's not many cities called Washington. So here I'm using a bidirectional LSTM to basically classify each word in the sentence to tell me whether it's a location, a person, or something like that. And I can use this later on to filter and find the right topic in the knowledge graph. I'm almost out of time, so I'll go to the last kind of signal, which is contextual signal. We talked about VCA, so audiovisual content, text, and the last one is, how do people actually watch this video? Say a user watches 4 videos in a row, and 3 of them are clearly about wingsuit flying. It's in the title, the image is clear, but the third one is called Rodeo It Is. Okay. And maybe the image isn't that clear, so we get very little signal. But the fact that it was watched in a session along with a lot of wingsuit flying is kind of a signal that this may be about wingsuit flying. It's not a very strong signal, but it's still a signal. You can look at search queries. You can look at a lot of things that can help put the video in context and give some signal about what it could be. Or, for example, also some pages that might embed the video. So I'm out of time, so I'll just finish quickly by saying all those signals are merged together, like different sources of signals. We rank them, and then we rate them with human raters that tell us, how good of a job we did. They help build the training set. And that's it. At the end, you've got a system where you know all the topics of every video, and you can use this all over the place in YouTube for better recommendation, structured navigation, and much more. Hope you enjoyed this talk. Thank you very much.